In this screencast, we're going to look at another use for Ksp where we are going to be able to decide at what concentration a particular substance will precipitate and which of the two solutions it could possibly be in would precipitate first. Here's a situation for this particular type of problem. You will be given two different substances that are mixed in a beaker, and you will be asked to figure out which one's going to precipitate out first. What you're going to have to do is you're going to have to find the concentration of the ion for both conditions, and then compare the KSPs or the concentration values, and figure out which one is going to have the lower concentration, because the one with the lower concentration is going to be the one that is precipitating first. Here's our sample problem. It says a solution contains 1.0 times 10 to the negative second molarity Ag plus ions and 2.0 times 10 to the negative second Pb plus 2 ions. When Cl ion is added to the solution, both AgCl with that Ksp and PbCl2 with that Ksp precipitate from the solution, but they want to know what is the concentration of Cl needed to make those solutions precipitate, and which one of the two precipitates first. So you're looking at this problem and you have to do two simultaneous calculations and then determine which one has the lower concentration needed for it to precipitate first. Let's set this up. So we're going to do Ag on this side and we're going to do Pb on this side. We will know that the Ksp equals Ag ions times the Cl ions. And on this side we know that Ksp equals Pb ions times the Cl ions, but this is squared. Okay, that will help us as we work through this problem. We have some numbers. We're going to take our 1.8 times 10 to the negative 10th equals our Ag ions, so 1.0 times 10 to the negative second, and then our Cl. I'm going to draw a big old line down the middle here that's going to help us delineate. All right, and then on this side we have our 1.7 times 10 to the negative fifth equals our Pb, which is 2.0 times 10 to the where'd it go? Negative second, times our Cl squared. So we'll work this through. I'm going to get, for this side, I'm going to get Cl is 1.8 times 10 to the negative 8th. And on this side, I am going to eventually get a Cl that is 8.5 times 10 to the negative 4th. No, that's the Cl squared. Sorry. Cl would be 2.9 times 10 to the negative second. And these are both in molarity. So we need to compare the concentration of the AgCl over here with the concentration of the PbCl over here. And we need to decide, these are the concentrations where they will precipitate. So the first part of the question was what concentration of Cl is needed. So we need to have, on the left side, we need to have 1.8 times 10 to the negative 8th molarity to make that happen. And on the right, we need 2.9 times 10 to the negative 2 to make that happen. So the second question is we need to figure out which one's going to precipitate first. So the one with the smaller concentration will precipitate first. So let's look. We have 1.8 times 10 to the negative 8, and we have 2.9 times 10 to the negative 2. The smaller number is the AgCl. So the answer for which one's going to precipitate first is the AgCl will precipitate first, and it will do so when the concentration is 1.8 times 10 to the negative 8 molarity. What would we be able to use this for? So when you're doing a lab, if you continue to add concentration of chloride ion to a beaker that has the two ions, you would be able to collect all the AgCl at that particular concentration. And as you approached the second concentration, then you would know that that is no longer Ag. All the Ag has been precipitated out of the solution. You would be then, as you got closer to the 2.9 times 10 to the negative second, you would begin to start precipitating out the lead.